Okay, back to symmetry. So the origin symmetry is a rotation symmetry 180 degrees. All right, so that's what it looks like. And then the first one, the x-axis, if it's symmetric with the x-axis, it's not a function, and we don't talk about functions as much, but still we want to just be aware of this type of symmetry. And let me grab a marker real quick. So if it's symmetric with the x-axis, it has to be a sideways graph. One of those special cases we said not a function, like a sideways parabola where x equals y squared. X equals y squared is a sideways parabola, and it would fold along the x-axis, and if I drew it well enough, those two curves should meet. And then x equals absolute value of y is our sideways v. So it has symmetry with the x-axis. So if something has symmetry with the x-axis, it's actually not a function. All right, now let's go one step further. Now that we kind of know what the symmetries look like, either fold along the x, fold along the y, or they rotate 180 degrees and they match up with themselves is the idea for symmetry. How can we determine symmetry algebraically if it's not a function we know? So the rule is, the official rule, and if you're following along in 2.7, reading the rule for symmetry, officially it says to check for y-axis symmetry if all the x's can be changed to a negative x and no change is made for y. You get the same y value whether you put in x as negative x or positive x, you come out with the same result. Then that proves the y-axis symmetry. So look at this, y-axis symmetry, our examples we have here. If you change this x to negative x, and we could show it with the t-table, whether you have positive 2 squared is 4 or negative 2 squared is 4, you get the same result. Y equals absolute value of x. Whether we put in 3 or negative 3, you get the same result for y. And then x to the fourth example I had, it doesn't matter what value you put in, positive or negative, you get the same result for y. So that's how you check. So say you had an equation like y equals 3x to the third plus 2x squared plus 5x minus 7. That thing's not going to have symmetry with the y-axis because even though this x squared I could change to negative x squared and it wouldn't matter. I've got a cube and to the first. There's other things on there that's going to make it the negative sign affect it. But if I had a line of terms and only positives, not positives, but only even exponents, 5x to the fourth, 3x squared, 2 with an absolute value of x, and a plus 2 on the end, then I'm fine. If x is negative or positive to the fourth, it's fine. Here again, and then that one doesn't have a variable, so it's just a constant. So it wouldn't matter if x is positive or negative. If you made a t-table, you'll get the same result for y. So this has y-axis symmetry. So again, you wrote down, if x is changed to negative x, you get the same result for y, then it is confirmed algebraically. And another thing they'll call this is an even function. This is known as an even function, and you can kind of see why. If all the exponents are even, that's considered an even function. Anytime it's got y-axis symmetry, it had to be an even function. All right, the origin symmetry. No, I think I'll do x-axis next, because it kind of flows with this. The x-axis symmetry is the opposite of what I just did. For x-axis symmetry, it's if you change the y to negative y and no change to x. It has no effect on x. That proves x-axis symmetry. So just the opposite here. So now looking at, and these are the ones that are non-functions, the top of the board. If you have x equals y squared, we know that's a sideways parabola, a non-function. But notice whether y is positive y or negative y, you get the same output for x. Whether y is 7 squared is 49 or negative 7 squared is 49. Same x value regardless of the sign of y. So if you change all the y's to negative y, it matters not. That proves x-axis symmetry. And then lastly, the origin symmetry. For origin symmetry, you change x and y. So if you wanted to prove it algebraically, you go back through the equation, change every x and every y to the negatives of themselves, and see if it's an equivalent outcome algebraically. Change x and y to their negatives and see if it's equivalent. For example, y equals x cubed we know is an origin symmetry, has origin symmetry. If I change y to negative y and this x to a negative x, the negative y is just, there's nothing to do there. There's no squaring of it to make it positive or anything, so it stays negative. This negative is cubed, so it stays negative. Then we could divide both sides by -1, and we get back to where we started. Also, we could make a t-table and show some values that it works every time. With any value, you get the same result. If you plug in, changes both to their negatives, you get the same. It's a symmetric point on quadrant 1 to quadrant 3, or quadrant 2 and quadrant 4. They have symmetric points when you change both their signs. This will always happen when you notice these are all odds. We have x to the third, x to the first, cube root of x. So anytime you have all odd exponents, which we're going to call this one an odd function, so origin symmetry is called an odd function for that reason. And you'll be able to see, even if it's an equation you're not familiar with, like y equals x to the fifth plus x to the third plus x to the first, all odd exponents, is going to be an odd function. This thing is going to have symmetry with the origin. If you change the y to a negative and all the x's to negative, it's going to be symmetric. Now, if you put a constant on the end of this and it shifts it up or down, it actually does lose its symmetry here. You'll see if you test that out, it will change. We'll change it a little bit. So, but that is the rule. Change all your x's to negative x's, change all your y's to negative y, redo the equation, see if it's equivalent algebraically, and then that proves it. Let me show you an example of one that has all symmetries. No, not that. Most of your examples have been translations or examples from your 10 basic graphs. But remember, we did this circle graph back in 2.2. So let me mention the circle to you. If you have just a basic circle, x squared plus y squared equals 16, that is a circle centered at the origin. It's not moved from the centering of the origin. There's no offset numbers here. So it's centered at 0, 0. The radius is 4, so it'd be out 4 all around it. That thing would have all the symmetries here. We could show it just looking at the graph. It folds this way, it folds this way around the y-axis, and you can rotate it any amount if it's centered at the origin like this, and it has all the origin x-axis, y-axis symmetry. Also, algebraically, we would check it to see if it has, going through our list, x-axis, you change the y to a negative y. If that's negative y because it's squared, it doesn't matter. It's equivalent. All right, then to check for y-axis, you change this x to negative x. Because it's squared, same outcome. It does not change it. And then to check origin, which we've kind of already done, if you have x-axis and y-axis origin, x-axis and y-axis symmetry, you're going to have the origin because you've kind of checked each of them. But just to be thorough, the origin symmetry, we would change both at the same time, the x and the y to their opposite. Then we can see if it's an equivalent algebraic equation, or if we were to plot points, would we get the same outcomes? And yes, we would. The negative squared on this. Now, if it had the offset, and I'll do one like that next, then it would lose its symmetry with, I guess, all of them. It depends on how it's shifted. We'll look at that in a second. But anyway, that one has all 3 symmetries. A circle centered at the origin would have all of its symmetries. Now, not all circles are centered at the origin. So let's say we had an offset. Just to remind you, when it's in this form, you shift it. This is your x shift and your y shift. We do the opposite sign. And you might notice this kind of falls in line with our lecture earlier where we did the translations. You do the opposite when it's in a parenthesis grouped, was a rule for horizontal translations. So it sort of applies here, right? When it's in parentheses grouped with the action, we do the opposite. So it's a +3 shift and a -1 shift. That's the new center of this circle. And then its radius is 4, the square root of the number on the end. So what would this look like? Moving it over 3 and down 1. That's my center. And then up 4, go 4 around all that. So it is a very symmetric figure, so don't get me wrong there, but it just is no longer symmetric, so I can't fold it along the y-axis and it meet exactly, right? There's just a little bit over there and a lot over here, so it's no longer that way. And then this way, if I fold it here, it's offset too far down, it's lost that symmetry too. And then it doesn't rotate around the origin exactly the same. So it lost its symmetries officially with this, even though it's still a very symmetric figure. If you put a new XY axis over here, it has symmetry, but it's shifted symmetry, so it doesn't fit in what we're discussing for just this lesson now.